So this unit of mechanics that we're working on at the moment is all to do with equilibrium. So we started looking at equilibrium in systems of forces, and now we're looking at systems of forces where there's a potential that the system could turn. So in equilibrium, we've got the same equilibrium we were dealing with previously, where the sum of the resultant forces in the x direction, the y direction must equal 0, but also if it's in equilibrium it's not going to turn. So it gives us a second set of equations that we can generate to do with the sum of moments. So Eg5. A uniform beam of length 2 meters and mass 4 kilograms has a mass of 3 kilograms attached at one end and a mass of 1 kilogram attached at the other. Find the position of the support if the beam rests in a horizontal position. Let me get myself a ruler to draw my beam. Okay, so there's my beam, and that's going to be resting on a point, and we don't know what that point is. It's telling me it's a uniform beam. That's key because that means that the center of mass of the beam can be situated at the middle of the system, at the middle of the beam. Okay, so uniform beam, center of mass at center of beam. So we can put on here roughly where it looks about halfway. It's a mass 4 kilograms. It's a force diagram. So it's a 4G force acting there. It tells me I've got a 3 kilogram mass at one end. So it's got a force pulling down there of 3G and a 1 kilogram at the other end. So a 1G mass acting there. And then there's one more force to add to that diagram, which is a resultant force. We have a contact there between the pivot and the beam, so consequently we will have a reaction force acting like that. So those are all the forces. Now we need to put on what distances we know. We know that we've got a uniform beam of length 2 meters, and we want to find the position of that. So if we want to find that from this end, if we say that that is a distance x, then we also know that from here to here is a distance of 1 meter. So this is a distance of 1 minus x, and that's a distance of 1 meter, like that. So those are the distances that we're dealing with. Now if we take one end of that to be A, let's say that point there is A, we'll take our moments from there. But because it's in equilibrium, or because we need it to be in equilibrium, then sum of the y components must equal 0. There's no forces acting horizontally, so it's the horizontal forces must equal 0 plus the sum of those moments must equal 0 as well. So if we work with the forces first of all, then I know that I've got R minus 3g minus 4g minus 1g must equal 0. So R will be 8g. So that resultant force has to balance downward forces, so it's equal to 8g newtons. We can leave it like that for a moment. Then we take the moments about A. So from A, 3g is not going to have a moment because it's a distance of 0. Put it in, just so we know we've dealt with each force. So I've got 3g times 0 plus, and then I've got this r. Now this r, if I'm pivoting from there, is going to try and turn that in an anti-clockwise direction. So it'll be minus r times distance x. Then I've got the 4g force, which will be turning clockwise. So that will be 4g times a distance of 1 meter plus 1g times a distance of 2 meters. And I know that this is an equilibrium, so that has to equal 0. So I've got 1, 2, 3, 4 forces within that system. So I've got 1, 2, 3, 4 forces within my moments equation. So I know that I've dealt with everything I need to deal with. So I can simplify this now. The 3g times 0 is going to go. I know that r is 8g. I know it's negative, so if I had that taken over, it would be positive. So I have 8gx equals 4g plus 2g. So 8gx equals 6g. G's will cancel. So I have x equals 6 over 8, which is 3/4. So it's going to be 0.75 meters away from that 3 kilogram mass. So I've drawn the system like that. There's no reason why we had to. We could have had the 3 and the 1 the other way around. We could have had the pivot over there. It doesn't matter. But once we've identified where we're taking the moments from, that will then give us the distance that we're working with. So 0.75 meters from 3 kilogram mass. And because it's clear the way that we've drawn that and all the information's on there, that's unambiguous.